Welcome to the API 571 Audio Masterclass series. This episode is brought to you by Mag Integrity. For the complete, high-resolution study guides, API 571 exam prep question banks, and to unlock our full private audio library, visit our premium engineering portal at magintegrity.ca.
Hey, it's great to be back here for another deep dive.
Yeah, I'm really excited for this one. So to start us off, I want you to just imagine a massive, high-pressure refinery vessel.
Oh, okay, setting the scene.
Right. So this vessel, it's been operating flawlessly for, say, 20 years.
Wow, 20 years. That's a good run.
Exactly. No leaks, no pressure drops, no warnings whatsoever. It is universally considered to be perfectly safe.
Right. Everyone's happy.
But the exact moment your operations team shuts it down for a mandatory routine safety inspection.
Just standard turnaround.
Exactly. The moment they pull the heat away to let humies inside to do their jobs, the steel of that vessel secretly turns into glass.
Yeah, it's terrifying.
It really is. Today, we are hunting a metallurgical ghost.
And I would argue it is one of the most insidious ghosts in the entire field of asset integrity.
Definitely.
Because it just completely breaks all the, intuitive rules of mechanical degradation that we're used to.
Exactly. I mean, normally when you and I talk about mechanical failure or, metal degradation, there's a physical trail of breadcrumbs, right?
Right. There's usually evidence.
Yeah. We look at a rusting pipe, or we put a pick gauge on it, we measure the thinning metal, and we can mathematically say, here is the problem, and here's exactly when it will fail.
It's very tangible.
Yeah.
You can run an ultrasonic thickness scan out in the field and actually see the remaining wall.
Right.
You can just calculate your corrosion rate from there.
But the diagnostic landscape we're stepping into today is completely different. It's totally invisible to the naked eye.
Oh, absolutely. And practically invisible to standard non-destructive testing, too.
Right. So we are zeroing in on the official API RP 571 documentation today.
Section 3.1 specifically.
Yep. And our mission for this deep dive is to completely deconstruct the damage mechanism known as 885 degrees Fahrenheit, or 475 degrees Celsius embrittlement.
It is a mouthful, but it's a critical one.
Definitely. And to be clear for you listening, we're not just reciting the code today.
No, absolutely not. That would be dry.
Right. We are going to translate the intense atomic level metallurgical theory behind this into the exact uncompromising field realities that you, the integrity engineer or inspector, are going to face during your next turnaround.
Because, if you don't understand the underlying physics of how this mechanism operates, you just have absolutely zero chance of anticipating where it's going to strike next.
And when it does strike, it's not polite about it.
No, it doesn't give you a small, polite leak. It gives you a catastrophic, sudden, brittle fracture.
Okay, let's unpack this.
Sure.
We need to start at the absolute foundation of the science here. What is actually happening to this steel?
Well, the API 571 text notes that this is fundamentally a time-dependent loss of toughness.
A time-dependent loss of toughness.
Right.
And I want to clarify that for our listeners because they're out there dealing with yield strengths and tensile strengths all day.
Right. Strength is usually the focus.
Exactly. So we need to be explicit that we are talking about toughness, not just strength.
That is a critical distinction to make right out of the gate, I think.
Yeah.
Because in physical metallurgy, strength is just a material's ability to withstand an applied load without yielding or breaking.
Right. How much weight it can hold.
Exactly. But toughness is the material's ability to absorb energy and actually deform plastically before it fractures.
Right. So if we step away from, the dry spaghetti analogy that gets tossed around in basic training classes,
Yeah.
we can look at this in terms of actual industrial materials. Think of a polycarbonate face shield versus, say, a sheet of tempered glass.
Oh, that's a much better way to frame it for this context. I like that.
Thanks. So if you take a heavy steel ball
Yeah.
and drop it on the polycarbonate shield, the shield might dent, right?
Right. It'll gouge or warp, maybe.
Yeah, but it absorbs the kinetic energy through plastic deformation. It yields, and that is toughness.
Exactly.
But if you drop that same heavy steel ball onto a sheet of tempered glass, the glass doesn't dent at all.
No, because it has incredibly high compressive strength.
Right. But it has almost zero toughness. So instead of absorbing the energy and yielding, it just instantly shatters into 1,000 pieces.
And what 885 degrees Fahrenheit embrittlement actually does is it slowly, over years of service, fundamentally changes the crystalline structure of your flexible, energy-absorbing polycarbonate-like steel into that rigid, unforgiving glass.
But how does it do that? I mean, the code says this is a creeping degradation that takes years to develop in service.
Right, it's not fast.
So it's not like an instant chemical attack, like an acid washing over the metal.
No, it's something happening entirely inside the metal itself.
Inside the crystalline lattice.
Yeah, it all comes down to phase separation at the atomic level.
Okay, phase separation.
Right, so when these susceptible alloys are manufactured at the mill, they are solid solutions. At room temperature, the atoms of iron and the atoms of chromium are just mixed perfectly together in a stable crystalline lattice.
Like soap dissolved in water.
Exactly. But when you subject these specific alloys to long-term exposure at elevated temperatures, you provide just enough thermal energy to allow the atoms to start moving.
They immobile.
Yeah, they get mobile. Because thermal energy is really just atomic vibration, right?
Right. Heat is just movement at the atomic scale.
Exactly. And at these specific operating temperatures, the chromium atoms actually begin to slowly migrate through the iron lattice.
It's drifting through.
Yep. And the solid solution becomes thermodynamically unstable, so it begins to separate into two completely distinct microscopic phases.
Okay, so what are these phases called?
You get an iron-rich phase, which metallurgists call the alpha phase, and a chromium-rich phase, which is known as the alpha prime phase.
Okay, so the metal is slowly unmixing itself. It kind of sounds like a vinaigrette salad dressing that's been left sitting on the counter.
That's precisely it. The oil and the vinegar separate.
Right.
But here is the major structural problem with that happening inside solid steel.
Okay, what is it?
As that chromium-rich alpha prime phase precipitates out, it doesn't just sit there harmlessly in the lattice.
Right, it has physical volume.
Exactly. These new microscopic structures act as literal roadblocks within the crystal lattice of the metal.
Okay, let's see if I have the mechanics of this right, because I want to make sure I'm picturing this correctly.
Go for it.
When a normal, tough piece of steel is subjected to an impact or a massive stress, the way it absorbs that energy is by having its microscopic crystalline layers slide over one another.
Yes, exactly. Those are called slip planes.
Slip planes. Okay, so that sliding is what we see on a macro scale as bending or yielding.
Exactly right.
So if the chromium has clumped together into these new alpha prime precipitates, is it essentially like dumping a handful of jagged sand into a perfectly greased ball bearing?
Wow, yeah. That is exactly what is happening mechanically.
Just grinding it to a halt.
Yep. Those alpha prime precipitates physically lock up the slip planes.
Oh, wow.
So when a sudden mechanical or thermal stress is applied to the metal later on, the crystalline layers try to slide to absorb the energy, just like they're supposed to.
They can't.
They can't. The alpha prime roadblocks stop the movement cold.
Because the sand is in the gears.
Exactly. And because the energy has absolutely nowhere to go and the metal can no longer yield, the atomic bonds simply tear apart. You get a sudden catastrophic cleavage fracture.
And we call this damage mechanism 885 degrees Fahrenheit or 475 degrees Celsius embrittlement, simply because that is the absolute optimum temperature where this specific metallurgical sabotage peaks.
Correct. It's the temperature where the atomic mobility and the thermodynamic drive to separate are perfectly balanced to cause this degradation at its maximum possible rate.
The sweet spot for disaster.
Exactly. But we have to make sure listeners understand that 885 degrees Fahrenheit is really just the peak of the bell curve.
Right. It's not the only temperature it happens at.
No, not at all. The actual kinetic danger zone is a much wider band, which we will define strictly when we look at the operational envelopes a bit later.
Okay, we'll definitely get to that.
Okay.
But this brings up a massive glaring question for me.
Okay, what is it?
If this phase separation is happening inside the metal, changing its fundamental nature over years of operation, why can't the inspection department just go out there and look for it?
Ah, yes.
I mean, if it's changing the metal, shouldn't we be able to see it?
Well, what's fascinating here is that this is what we call the metallographic detection paradox.
The paradox. Explain that.
API 571 makes a definitive, uncompromising statement here. This damage mechanism is exceptionally difficult to find prior to the actual failure of the equipment.
It doesn't show up as uniform wall thinning or anything?
No, there is absolutely zero metal loss associated with 885 embrittlement. None.
Zero.
Literally zero. I mean, think about it. If a refinery installed a fractionator tray with a 1/4-inch thickness back in, say, the early 2000s,
Okay.
and it has been suffering from severe 885 embrittlement for 2 decades, a thickness check today will still show a perfect 1/4 inch of metal.
Wow.
Yeah, there's no external corrosion, there's no pitting, no scaling, no blistering, nothing.
It looks brand new.
Basically, yeah.
Yeah.
Because the physical degradation only affects how the metal absorbs energy, the internal atomic arrangement.
Right, the slip planes.
Right. It doesn't affect the physical geometry of the component itself at all.
It doesn't eat away the wall thickness.
Exactly. The degradation is entirely microstructural. It drastically reduces the toughness without altering the physical dimensions or the weight of the part.
Yeah. That is wild.
Yeah, you are looking at a perfectly intact, beautifully smooth piece of steel that has secretly become as brittle as glass.
That is a terrifying reality for anyone, signing off on the mechanical integrity of a unit.
Oh, absolutely. It keeps you up at night.
Because if we can't visually see the damage and we can't measure it with standard thickness gauges, it means we absolutely have to know where to look ahead of time.
Exactly. We have to know exactly which alloys are susceptible so we can flag them long before they break.
Okay, so let's get into the specific materials then, because this is critical.
It really is.
If you are listening to this right now and pulling up your equipment registers, what exact materials do you need to be hunting for?
Well, the API text is incredibly specific regarding the hit list. And the primary victims are the 400 series stainless steels.
The 400 series, okay.
Yeah, but this is where you have to pay really close attention to your material test reports because they are definitely not all created equal.
Right, there are a lot of grades in the 400 series.
Exactly. The code specifically lists grades 405, 409, 410, 410S, 430, and 446.
Okay, let's break down the chemistry here. Because the risk profile basically comes down to a very specific elemental threshold, doesn't it?
It absolutely does. The alloy composition is the ultimate determining factor for susceptibility.
And specifically, which element?
It is the exact chromium content, the CR percentage.
Chromium, right.
Remember the metallurgical theory we just discussed? The formation of that brittle alpha prime phase is driven by chromium literally separating from iron.
Right, the vinaigrette separating.
Exactly. Therefore, the amount of chromium available in the alloy fundamentally dictates how much of this brittle phase can physically form.
So, generally speaking, more chromium equals more potential for embrittlement.
In the context of ferritic stainless steels operating in this temperature band, yes, exactly.
Okay.
And API 571 draws a very clear line in the sand here, dividing these 400 series alloys into two distinct risk categories based purely on their chromium thresholds.
Okay, let's start with the lower risk category then. Which ones are those?
The lower chromium alloys listed in the text are 405, 409, 410, and 410S.
And what's their chromium percentage?
These alloys typically hover around the 11% to 13% chromium mark, maybe just a little bit higher for 409.
Okay, 11 to 13%.
Yeah. And the code explicitly states that these specific grades are significantly less susceptible to embrittlement.
Significantly less susceptible, but less susceptible doesn't mean immune, right?
No, it definitely does not mean immune.
Okay.
It simply means the kinetics are slower, and there is just less raw chromium available in the matrix to form massive, continuous networks of that brittle alpha prime phase.
Got it. So they degrade, but slower.
Exactly. They might still suffer some degradation over incredibly long time frames, but they are not the primary bad actors in the plant.
Right. And then we have the heavy hitters, the highly susceptible grades.
Right. The higher chromium ferritic stainless steels.
The dangerous ones.
Yes. The text points out that these are much more susceptible, and it defines the exact chemical makeup that pushes them into that danger zone.
Which grades are we talking about here?
We are talking about type 430 stainless steel, which contains between 16% to 18% chromium.
Okay, 16 to 18.
And then there's type 446 stainless steel, which contains a massive 23% to 27% chromium.
Wow. 27% chromium is a huge amount of alloying element to just have sitting in the matrix.
It is a ton. And at those high concentrations, when the temperature is right, the precipitation of the alpha prime phase is incredibly rapid and extensive.
Because there's so much chromium ready to separate.
Exactly. The brittle networks form very quickly, and they completely dominate the microstructure.
So if you have 430 or 446 operating in this susceptible temperature band, you are basically in the highest possible risk category for this failure.
You are absolutely at the top of the risk matrix.
Okay, so if you're combing through piping specs, anytime you see 430 or 446, those chromium percentages should immediately trigger a red flag for you.
Definitely.
But the 400 series isn't the end of the story, is it? Because the code also pulls Duplex stainless steels into this.
It does, yeah.
Yeah.
And for very good reason. Duplex stainless steels are definitely on the hit list.
Which ones specifically?
The text explicitly names alloys 2205, 2304 and 2507.
Okay, I have to push back here for a second, or at least play devil's advocate for the listener.
Sure, go for it.
Because engineers use duplex stainless specifically because it's a high-performance material.
Wow, absolutely. It's fantastic.
It gives you fantastic yield strength and, incredible resistance to things like chloride stress, corrosion, cracking. It's an expensive premium upgrade in a lot of refinery applications.
Very expensive.
So why is a premium material suddenly a massive liability here?
It all ties back directly to that chromium rule we just established.
Percentage of chromium.
Right. To get those incredible high-performance properties, particularly the amazing corrosion resistance, duplex alloys are heavily alloyed with chromium.
Oh, okay.
And by definition, a duplex stainless steel has a mixed microstructure. It is roughly 50% austenitic and 50% ferritic.
And it's that ferritic half of the matrix that is the problem.
Exactly. The austenitic phase is largely immune to this specific mechanism, but the ferritic phase is highly vulnerable.
And how much chromium is in that ferritic phase?
Well, the text notes that these specific duplex alloys contain critical matrix thresholds of 22% to 25% chromium.
Wait, 22 to 25%, which puts them right up there in the exact same danger bracket as the Type 446 ferritic stainless steel we just talked about.
Precisely. Because that chromium content in the ferritic phase of the duplex is so high, 22 to 25%, these duplex alloys are classified by API 571 as much more susceptible.
Wow.
Yeah. The premium corrosion resistance you paid for comes with the severe penalty of high susceptibility to 885 embrittlement if you put it in the wrong temperature service.
That's a brutal trade-off. Okay, here's where it gets really interesting for me.
Oh, yeah.
Because when I was reviewing the code for this deep dive, there was a glaring contradiction regarding austenitic stainless steels, specifically the 300 series weld metals.
Ah, the welds. Yes.
Right, because the text firmly establishes that this is a problem for ferritic microstructures. So 300 series stainless like 304 or 316 piping, which are fully austenitic, should be completely immune. Right.
The base metal of a 304 or 316 pipe is indeed immune. Austenitic crystal structures do not undergo that alpha to alpha prime phase separation at these temperatures.
Okay, so the pipe itself is fine.
The pipe is fine, but the text highlights a massive counterintuitive vulnerability when you actually have to weld those pipes together.
Because welding 300 series stainless creates a completely unique metallurgical problem. Let's explain why that is.
Well, when you weld 300 series stainless steel, you are obviously melting the metal.
Right.
As that weld pool cools and solidifies, if the resulting weld deposit is purely 100% austenitic, it is highly prone to microscopic tearing.
Tearing as it cools.
Yeah. The thermal contraction stresses during solidification actually cause the grain boundaries to pull apart.
Yikes.
It's a severe fabrication defect known as hot cracking.
And you obviously cannot put a pressure vessel or a high-temperature pipe into service if the weld seams are full of microscopic cracks.
You absolutely cannot. So to prevent hot cracking, welding engineers do something very specific.
What do they do?
The weld filler metals, the consumables you use to make the weld, are chemically engineered so that the resulting weld deposit is not purely austenitic. It is actively engineered to contain a small, highly controlled amount of the ferrite phase.
And API 571 gives us the exact number for this, right?
Yes, it does. The text specifies that to prevent hot cracking during welding, these 300 series welds normally contain up to about 10% ferrite phase.
Up to 10% ferrite.
Right. That small amount of ferrite acts as a sponge for impurities and essentially disrupts the straight grain boundaries, completely preventing the hot cracking.
So we intentionally engineer ferrite into an otherwise totally immune austenitic piping system.
Yes.
It's like a metallurgical pharmaceutical.
Oh, that's a good way to put it.
Right. You take a powerful medicine, the ferrite, to cure one fatal disease during fabrication, which is the hot cracking.
Right.
But the side effect of that medicine is that you just permanently introduce the ferrite phase into your system, leaving you entirely vulnerable to a long-term chronic disease. 885 embrittlement.
That is exactly the reality. The very presence of that up to 10% ferrite phase, which was intentionally designed into the weld to keep it structurally sound on day one, is the exact critical factor that actively invites 835 degrees Fahrenheit embrittlement over the next 20 years.
That is just wow.
Yeah. The 304 base metal of the pipe might be perfectly fine retaining all of its toughness, but the weld seams connecting the pipes are secretly slowly turning into brittle glass.
That is wild. You solve an immediate fabrication problem, but accidentally engineer a long-term asset integrity time bomb into every single weld joint.
Pretty much.
Which leads us perfectly into the operational realities, because we know exactly which materials are at risk now.
Right, the 400s, Duplex, and 300 series welds.
Exactly. Now, we need to map out the exact operational parameters our listeners need to be tracking.
Yeah.
What is the actual time at temperature kinetic profile for this failure?
Well, we already established that 885 degrees Fahrenheit or 475 degrees Celsius is the peak of the embrittlement curve, right?
That's where the degradation happens the fastest.
But the API text explicitly defines the actual kinetic danger zone as exposure to temperatures in the 600 degrees Fahrenheit to 1,000 degrees Fahrenheit range.
Or 370 degrees Celsius to 540 degrees Celsius.
Correct. If your susceptible metal, whether it's a 440 stainless tray, a 2205 duplex pipe, or a 347 stainless weld with 8% ferrite, is operating anywhere within that 600 to 1,000 degree Fahrenheit band, the clock is ticking.
The alpha prime precipitates are forming.
They are forming.
And the code makes a very pragmatic, almost ruthless point about how we have to treat equipment out in the field regarding this time exposure.
Oh, it basically removes all the guesswork. API 571 states that, as a practical matter, because refinery equipment is typically in service for years at a time without interruption, the standard field assumption must be that any susceptible materials that have been exposed to temperatures in this 600 to 1,000 degree Fahrenheit range are affected.
Wow. So you don't assume you got lucky.
You absolutely do not.
You don't assume the kinetics were slow.
Nope. If it is the wrong material and it has been soaking in that heat band for years, your baseline assumption as an inspector or engineer is that the embrittlement has already occurred.
The toughness is just gone.
The toughness is gone.
Okay, I have to push back here on the mechanics of this, though, because this is where the logic seems to break down for someone actually walking the plant.
Okay, let's hear it.
If I have a piece of 446 stainless steel operating at 800 degrees Fahrenheit for 10 years,
Yep.
You are telling me the alpha prime phase has fully precipitated.
Yes.
The metal is fully embrittled. It has the toughness of glass.
Correct.
Then why doesn't the equipment just shatter right then and there while the plant is running? I mean, it's under hundreds of pounds of pressure. There's thermal expansion happening, fluid flow vibration. Why doesn't it just blow apart during steady-state normal operation?
This is the exact question every single engineer asks the first time they encounter this mechanism.
Right. Doesn't seem to make sense.
It is the crux of why this phenomenon is so incredibly deceptive. If we connect this to the bigger picture, the code provides a crucial insight here. The effect on toughness is actually not pronounced at the operating temperature.
Wait, really? The brittleness doesn't exist when it's hot?
It's not that the microstructural damage disappears, but rather that the heat actively masks the symptom.
Oh.
When the metal is sitting at 800 degrees Fahrenheit, there is so much ambient thermal energy in the system that the atoms still have enough mobility to physically slide past those alpha prime roadblocks we talked about earlier.
Oh, I see.
So at high temperatures, the material actually retains enough ductility to behave safely under normal operating stresses.
Yeah. So the high heat actually acts as a buffer. It keeps the metal somewhat forgiving, even though the structural damage is fully developed.
Exactly. In metallurgical terms, what 885 embrittlement actually does is it shifts the ductile to brittle transition temperature, the DBTT, dramatically upward.
Okay, the DBTT.
Right. But as long as your operating temperature stays above that new higher transition temperature, the metal behaves in a ductile manner.
Okay, so when is the danger actually triggered?
The danger is triggered the exact moment the temperature drops.
When it cools down.
The text explicitly states that the massive loss of toughness becomes incredibly significant at lower temperatures.
Right.
When the operations team cools the unit down, that thermal forgiveness vanishes. The atomic mobility drops, the metal crosses below that elevated transition temperature, and the true brittle nature of the degraded microstructure instantly takes over.
This is what we call the temperature trap.
Yes.
A catalytic reformer or a hydrotreater unit might run perfectly, safely, without a single issue for 10 straight years at 850 degrees Fahrenheit.
Yep.
But the moment you cool it down for a critical process event, and the code specifically names plant shutdowns, startups, or process upsets, that is the exact moment the metal turns to glass.
Yes. The vulnerability is almost entirely tied to transient cooling events.
Which means we really need to look at the massive refinery impact this has.
Yeah.
How does this theoretical temperature trap translate to the physical equipment in a facility?
Well, what is particularly challenging about 885 embrittlement in the context of API 571 is that it doesn't isolate a single process unit.
It's not just one specific area.
Right. Like if you look at ammonium bisulfide corrosion, you know you're looking at the reactor effluent of a hydroprocessor.
Sure.
If you look at polythionic acid stress corrosion cracking, you know you're looking at sensitized equipment during a shutdown. But this section casts a much wider net.
Because it's purely a function of material chemistry and operating temperature, regardless of what process fluid is inside the pipe.
Exactly.
It could be crude oil, it could be hydrogen, it could literally be a vacuum. The metal doesn't care.
The metal absolutely doesn't care. The field reality is that any equipment constructed from the listed susceptible alloys is at risk if it falls in the temperature band.
So what are some common examples?
Well, the code points to components that are traditionally made of high chromium ferritics for sulfidation or oxidation resistance. We're talking about fractionator trays in crude and vacuum units.
Okay.
We're talking about cyclone components in FCC units.
And we're talking about reactor internals, heat exchanger tubes, and, extensive piping networks, especially when you factor in the duplex alloys in those 300 series welds.
Right. If any of that equipment has been soaking in the 600 degree to 1,000 degree Fahrenheit range for years, it is deemed affected.
And we have to emphasize to you, the listener, how this fundamentally alters the risk profile of your plant during turnaround season.
Oh, massively.
The equipment survives steady-state operation because of the temperature trap.
Right.
But think about what actually happens during a turnaround.
Right.
The operations team starts pulling the temperatures down to ambient so the maintenance crews can safely open the vessels.
Which means the material is actively becoming glass-like, just as the physical activities begin.
Exactly. You have intense thermal contraction across the entire unit. You have maintenance crews applying massive mechanical stresses. They are out there torquing bolts using hydraulic tensioners.
Well,
they're unbolting heavy flanges, inserting heavy steel blinds, and eventually hydro-testing the system with cold water.
that combination of ambient temperature and high mechanical stress is when a catastrophic brittle failure is most likely to happen.
It completely changes how you have to handle shutdowns, doesn't it?
It really does. You cannot treat a 20-year-old 430s stainless steel vessel or a highly aged duplex pipe the same way you treat a brand new one during a cool down.
You just can't.
No. The operations team has to be incredibly delicate with the thermal gradients, and the maintenance team basically has to treat the piping like it is structurally fragile until proven otherwise.
Which means, from an asset integrity standpoint, we desperately need to know if the damage is there before operations cools it down or maintenance stresses it.
Right.
We need to hunt it down. So let's look at in situ inspection and damage detection.
Okay.
If the danger is triggered the moment operations cools the plant down, then the maintenance crew's literal lives depend on knowing if the pipe is embrittled.
They do.
How on earth do inspectors check for that while the plant is still running hot?
I have to deliver the grim reality outlined in the API 571 text here.
Okay, lay it on me.
You asked how they hunt it down online. They don't.
They don't.
The text is definitive, and it draws a hard line in the sand. Online inspection is flat out not applicable.
None of it. I mean, we have incredibly advanced non-destructive testing today. Phased array ultrasonics, real-time radiography, magnetic particle.
Right.
Nothing works.
None of the standard NDT methods will catch the embrittlement itself prior to failure.
But why not?
Because, as we discussed with the metallographic detection paradox earlier, the damage is strictly microstructural. Ultrasonic testing looks for changes in acoustic impedance, like a void, a crack, or back wall metal loss. Radiography looks for density changes.
But 885 embrittlement doesn't manifest as metal loss.
Exactly. There are no voids, no thinning, and no macroscopic cracks until the exact second it breaks.
So standard in situ NDT scans looking for wall loss will literally print out a report saying the pipe is perfectly healthy.
Yes. It will give you a profound, dangerous, false sense of security.
Okay, so if we can't scan for it while it's running, and we can't use NDT to find the microstructural changes online, how do we ever formally prove it's there? Are we just guessing based on the thermometer and the calendar?
We aren't guessing, no. But the verification requires rigorous quantitative laboratory methods.
Laboratory methods.
Yeah. The text explains that the absolute most effective method of detecting or confirming 885 degrees Fahrenheit embrittlement involves physical destruction of the component.
Destruction.
Yes. You have to physically cut out and remove a sample of the suspect material from the actual equipment.
You literally have to cut a boat sample or a coupon out of your live pressure vessel or piping system.
Yes. You take the equipment out of service, you cut a piece out, and you send it to a metallurgical lab.
Whoa.
And once that sample is removed, it must be subjected to specific mechanical tests. The code explicitly points to impact testing, such as the Charpy V-notch test or bend testing.
Let's explain the Charpy V-notch test for a moment, just so the reality of this testing lands for everyone listening.
Sure.
They take the piece of metal you cut out of your refinery, they machine it into a small, precise rectangular bar, and they cut a V-shaped notch into the middle of it.
Right.
Then they put it in a machine with a massive, heavy pendulum.
And they just swing the pendulum down to smash into the back of the notched sample?
Exactly.
Okay.
And the machine literally measures exactly how many joules of kinetic energy the metal sample can absorb before it snaps in half.
Yep.
And a healthy, tough piece of steel will absorb a huge amount of energy, slowing the pendulum down significantly as it tears and yields.
But a piece of steel suffering from 885 embrittlement will absorb almost no energy.
It just snaps.
The pendulum will smash right through it effortlessly, and the fracture surface will look crystalline and shiny, what metallurgists call a cleavage fracture, rather than the dull, fibrous tearing of a normal ductile failure.
But the code also highlights a highly specific, much simpler qualitative detail about these tests, right? It doesn't always have to be a heavily instrumented Charpy test.
That's right. The text states that failure during a simple bend test is the most common way this damage is practically confirmed.
A simple bend test.
Yeah. You take the coupon you cut out of the tray or the pipe, you put it in a hydraulic press or a vise in the lab to simply bend it over a mandrel.
And instead of folding and yielding like steel should,
It just forcefully snaps.
wow. That sudden audible snap in a simple bend test is your definitive confirmation that the alpha prime phase has taken hold and 885 embrittlement owns your equipment.
Exactly. It is the ultimate proof of the microstructural degradation.
Okay, so if the only way to conclusively prove the damage exists is to cut holes in our equipment and snap pieces of it in half, what can we actually do with this knowledge proactively?
Well, this raises an important question, doesn't it?
It definitely does. How do we manage an entire refinery based on this? Let's move into mitigation and prevention. What are the engineering and administrative solutions here?
Right. So since you cannot inspect for it online with NDT, API 571 states that strict awareness of susceptible equipment is your primary overriding tool.
It's an administrative control at its core.
Exactly. You have to comb through your piping specifications, your equipment data sheets, and your turnaround histories.
Right.
You have to locate every single piece of 400 series stainless, every piece of duplex piping, and every single 300 series weld deposit operating in that 600 degree to 1,000 degree Fahrenheit band.
And then what?
And you must flag it in your inspection database.
That awareness is what dictates your actions later on.
Exactly. If a piece of equipment is flagged for 885, the operations team knows they have to control the cooling rates meticulously during a shutdown.
And the maintenance team knows they cannot strike it with a hammer or hydro-test it with ice-cold water.
The awareness directly drives the safety protocols of the entire turnaround procedure.
And what about for new designs? If an engineering firm is designing a new hydrocracker or a new vacuum distillation unit today, how do we design this ghost out of future plants entirely?
We have to extrapolate on the very strict material selection limits provided in the API text.
Super what?
To mitigate this issue in new designs that will operate chronically between 600 degrees and 1,000 degrees Fahrenheit, engineers must actively avoid specifying the higher chromium ferritic stainless steels.
So you have to keep the 430 and the 446 completely out of that temperature band.
Yes. You also have to absolutely avoid the Duplex steels in that range.
But what if the process fluid requires some level of chromium for corrosion resistance? I mean, what if plain carbon steel isn't enough?
If a ferritic 400 series stainless steel is absolutely required for process corrosion reasons, engineers must purposely select the lower chromium alloys.
Oh, as we talked about earlier.
Exactly. They must specify 405, 409, 410, or 410S, which the text explicitly guarantees are significantly less susceptible to the aggressive phase separation.
Okay, that makes sense. But what about the welds? This seems like the hardest part to mitigate. We can't just stop using 300 series stainless steel piping altogether. It's the backbone of high-temperature refinery piping.
No, we absolutely rely on 300 series stainless. We can't get rid of it.
So what's the fix?
To mitigate the weld vulnerability, engineers must carefully and ruthlessly regulate the 300 series weld procedures. It is a delicate, uncompromising balancing act during fabrication.
Because you need some ferrite to prevent the hot cracking during the initial construction, right?
You do. But the absolute necessity for long-term integrity is keeping that ferrite phase strictly capped.
Chapter what?
You must ensure the welding consumables. The filler wire chemistry and the welding heat input procedures are designed to keep the final ferrite content at or below that roughly 10% threshold mentioned in the text.
So an inspector on a fabrication floor has to be constantly checking the ferrite number of the welds as they're being made.
Yes, constantly.
It's all about balancing the risks. You need just enough medicine, just enough ferrite to prevent the weld from cracking as it cools,
Right.
but not a single drop more. Or you invite massive 885 embrittlement decades down the line.
Exactly. It requires incredibly tight quality control, reviewing the chemical equivalents in the filler metals, and ensuring the welders adhere strictly to the qualified procedure.
Wow.
You are literally engineering the microscopic structure of the metal on the fly to thread the needle between two entirely different failure mechanisms.
That is just incredible. Well, we have covered a massive amount of highly specific atom-level metallurgical ground today.
I really did.
And we tied it directly to the harsh realities of turnaround execution. But before we sign off, I want to leave you, the listener, with a final lingering thought to mull over based on everything we've unpacked today.
All right.
Think about the ultimate tragic irony of this mechanism. A massive vessel sits in your unit, operating at 850 degrees for years, and because of the temperature trap, the heat keeps it ductile.
Right.
It is perfectly stable. But what if the very act of shutting that unit down for a routine mandatory safety inspection, the deliberate act of cooling it down to ambient temperature to make it safe for humans to enter, is the exact thermal trigger that forces the metal across its brittle transition temperature, causing a perfectly stable component to suddenly suffer a catastrophic failure?
It gives you chills.
It completely redefines what the word safe actually means during a turnaround.
It certainly makes you look at a cooling pipe in a whole new, much more cautious way.
That wraps up our technical deep dive on this mechanism. Don't leave your exam or your asset integrity to chance. Head over to magintegrity.ca right now to subscribe to our full premium library, download the Visual Slide Companion Pack, and master API 571. Until next time, keep your assets safe and your inspections rigorous.